All right, so looking at pH here. pH is essentially looking at how acidic or basic, another word for basic is alkaline. So how acidic or basic is a certain substance. Now, on the far end, like we say something is a 0 pH, we'd be saying like a battery acid. What that's really saying, it has a very high concentration of hydrogen ions. Another way of saying that, and it's a little less common way, is saying it's a very low combination of OH minus ions. So then basic, on the other side, most extreme being 14, like such as drain cleaner, would be the opposite. It'd be a low concentration of H plus and a high concentration of OH minus. Now, other examples of pH, you would see like lemon to be pretty acidic. Like essentially the neutral point is 7 because 7's in between 0 and 14. So water, it should come as no surprise because we're mostly made of water. Water is going to be considered your neutral substance. And then you got vinegar, coffee, and then on the other end of the spectrum, if you have like all your cleaning products, like soap, even like if you were to take like a stomach tablet, that's going to be something that's going to be basic. Now, why that would make sense, especially thinking like stomach tablets, that would be basic, is because stomach acid is acidic. So that's the idea of those stomach tablets. If your stomach is upset, if you eat a lot of spicy foods, spicy things are pretty acidic. So the idea of like you take like Pepto-Bismol or something that tries to like cool down that acidic environment, make that acidic environment. Cool down isn't the right word. It tries to make the acidic environment more basic so that your the pH is a little more balanced in your stomach. Even though the pH in your stomach is still more acidic than like, and say your bloodstream or something. Okay, so if I get my cursor over here. Looking at a little bit more of the math of this and what's on like especially this side here, I essentially sort of said this already, that higher up you go, the more alkaline you are, and again, alkaline would be more basic. The lower pH you are, that's more acidic. And again, this is concentration of hydrogen ions, and they're comparing it to distilled water. So again, pure water would be a pH of 7. Now, thinking a little bit more about where the H plus and OH minus comes from, is if you were to take water is H2O. Imagine if we were to break apart water. Well, water would break apart into H plus and OH minus. So think about it. If water were to, like this is where like if you had way more H plus, that'd be a sign that you're getting way too far off of like the balance of like H2O to something else. Versus if you have way too much OH minus, you're too far off of the perfect balance of H2O. So anyways, just where the H plus and OH minus comes from. Now, another really important thing to understand is that this is a base 10 scale. What that means is that if I say, hey, this is saying baking soda right here is a pH of 8, and again, pure water is a pH of 7. So you might think, oh, that must mean that it's not that big of a difference. Because it's base 10, baking soda is actually 1/10 as acidic as water. Another way you can represent 1/10 is 10 to the minus 1. In a similar way, if you look at like urine or milk, urine and milk are 10 times, or 10 to the power of 1, more times acidic than water. So then if you were to ask, hey, how many more times acidic is grapefruit juice? Well, what you would do is you would do your pH of 7, that's water, minus, grapefruit juice is about 3, 7 minus 3 equals 4, so 10 to the power of 4 times more acidic is what grapefruit juice would be. So just be comfortable doing those calculations. It isn't, I don't think, super complicated, but it's just, again, understanding it's a base 10 scale. Okay, now, different ways. So essentially the way I've been describing acids and bases is actually what we would call the Arrhenius definition of acids and bases. So there's a couple different ways we're going to go over how you could think of what an acid is. What Arrhenius is saying is that really what I've said so far. If you increase the concentration of H plus, higher H plus, that's what's going to be an acid. So an acid would be essentially anything. So like HA would be your generic acid. HA will break apart into, so an Arrhenius acid is anything that will break apart into H plus, and then A minus would just be any sort of anion. So it breaks apart into not just any cation, but specifically the H plus cation. Okay? And then the Arrhenius base would be anything that would increase the concentration of OH minus in an aqueous solution. Remember, aqueous means dissolved in water. Okay? So here would be BOH. This would be just your generic base, and it breaks apart into a cation and then the OH minus. And I'm going to show you another definition of acid to bases. But so remember Arrhenius. Remember, there's an H in Arrhenius. So you hear H, you see the H, think H plus. Okay. Now another way of thinking about an acid base, and we call this the Bronsted-Lowry definition of acid and bases, is that a acid is anything that donates a proton, and a Bronsted-Lowry base is anything that donates, or excuse me, not donates, anything that accepts a proton. Now, if you're like, what's the relationship between Arrhenius and Bronsted-Lowry? Well, consider this: a proton is just an H plus. Because if you think of like the Bohr model of a hydrogen atom, it would just have one energy level. You would have a proton and a neutron, and then just one electron. So let's say, this is just a stable hydrogen atom, but if you were to remove that electron, then all that would be left over is essentially just a proton. And then this neutron could just kind of linger around with this proton, or it could just dissociate or somewhere else. But the point is, that's where the H. That's the relationship between when you think of like an H plus and a proton. Okay. Now then, Bronsted-Lowry base is anything that accepts protons. Well, consider this. Like that. That's maybe a little less obvious. But let's take this example. Water here. Water is H2O, so water will donate a proton because it has two of those hydrogen atoms. So what happens is our water will donate, this H, right? This H is going to disappear here, and then, I say disappear. It doesn't literally disappear. It's actually going to go, let me represent it this way. It's actually going to travel to what is our base. So our base is going to accept that proton, which is really just a hydrogen atom, and then it's going to make an OH minus. So this would be, let's fill this in. This is an O, that'd be an N and three H's. So then this results into an OH, so that's your hydroxide ion, and then your N, and then four H's, which is your ammonium. Both of these are polyatomic ions that you should be familiar with, so far in the class. Now some just kind of notation. Acid donates the proton, base accepts the proton. Now the conjugate base is what was the conjugate acid. So OH, or hydroxide, right here, that is a conjugate base because it could then, notice how this arrow, these reactions can go in the forward direction, that arrow, or the backwards direction, this reverse arrow. And in the reverse direction, if you were starting with NH4 plus OH minus, OH minus would then act like a base, accepting this hydrogen. So this hydrogen could then reattach to OH minus, reforming H2O. And that would happen back and forth, okay, until you get to some equilibrium concentration of both. All right, now let's try to really sort of compare the two, Bronsted-Lowry and Arrhenius. And they're kind of one and the same. Basically, Bronsted-Lowry is the more general definition, and Arrhenius is the more specific definition. So a Bronsted-Lowry acid is a proton donor. So a proton is more general term than specifically an H+. There are more protons that can exist in the world than just an H+. In a similar way, there are more things that can accept protons. There's many anions that can accept protons. Not an OH minus is just one among many. This is a minus sign. Okay, so that's why this is more specific. That's more general. So if I were to show you if I were to show you some sort of acid and be like, is this a Bronsted-Lowry acid or Arrhenius? You should be comfortable being able to identify them. And then just a reminder, the acids you got to memorize for the final. We've seen these before, but just want to put those on your radar. Okay, so let's kind of let's go through here. Let's practice this idea of labeling acid-base, conjugate base, and then acid-base pair. So if you look here, you have acetic acid. So hint that this is going to be your acid. And another, like, other than knowing that that's acetic acid, the telltale sign it's an acid, acids will typically start with an H. They don't always, but that's a good typical sign. And then water here, water's tricky because water can sometimes act like an acid, other times it acts like a base, because water was that perfect 7 in the pH scale. So you can't assume water is a base, you have to look at the context. Because water here is clearly paired up with an acid, that's how you know water is going to be a base. So then what's going to happen is this H from acetic acid is going to attach to H2O, making H3O plus. So then we would call this, because this once was the base, this is now the conjugate acid. And then acetic acid is going to break apart into the acetate anion, because the acetate anion came from an acid. That's why we call it the conjugate base. Yeah. And when they ask the conjugate acid-base pairs, they're just saying, like, this would be a conjugate acid-base pair, and then water and H3O plus would be another conjugate acid-base pair. All right, so look at one more example. So we got our hydroxide anion, OH minus, plus HCO3 minus. So if you're looking at this, it's like, I wonder what, and this is going to make carbonate, CO3 2 minus, and H2O. Well, really just look here and see what could have become what. Like OH minus, well, clearly that became H2O. So how does OH minus become H2O? Well, it gained an H. So that H must have come from the HCO3 minus. And then that's why HCO3 minus becomes your carbonate. And then OH minus is going to accept it. So here, if you're accepting an H plus, you are a base. And if you're donating an H plus, you are an acid. There's no E in acid. Okay, so then that would make this here, because this was the acid, this is now your conjugate base. And then water, because water was acting like a base, because hydroxide, OH minus, was acting like a base, now water is your conjugate acid. Okay? So then if they ask for the acid-base pair, they would just be, essentially the opposites of each other. And understand what conjugate acid, conjugate base means. What this means is we could then reverse this reaction or this top reaction. We could then take H2O. We could take the H on H2O and reattach it to the carbonate to make HCO3 minus and OH minus. In a similar way, you could take the hydrogen from H3O plus and reattach it to the acetate, remaking the acetic acid. Okay. So there you go. That'll do it for the notes.